This is slide number 55 and I am your presenter Asloob Mudassar. Removal of object plane quadratic phase factor. First of all, I would like to show you which is the quadratic phase factor which is associated with the object plane, and that is given over here in equation number 77 on the left hand side, which is e to the power iota k over 2 z1, and within the parentheses we have zeta square plus eta square. So this quadratic phase factor, which depends upon the square of zeta square plus eta square, is actually the quadratic phase factor which is associated with the object plane. So how we can remove that one? If the object field u0 of zeta and eta is defined on a spherical surface, you see we are going to define the object on a spherical surface with the center of curvature lying at the center of the lens and having a radius equal to z1, that is we are going to define the input object on a spherical surface. Then you know that in the Fresnel diffraction formula we will see that that the quadratic phase factor I have just mentioned would not appear in the integral, and that will be omitted in the derivation of the Fresnel diffraction formula, so that will not appear. So this is the one way of a removal of the quadratic phase factor. Now let's look at the second possibility. Illuminate the object with a converging spherical wave with the focusing point aimed at the center of the lens. Fourier transform of the object field will appear at the pupil plane of the lens as shown. So this is the second way. You see that the plane wave are coming, they are incident on the lens, and the lens is producing a converging wavefront which will focus at the center of the second lens as indicated by the small dotted arrows, by the small dotted lines. So you see that we have placed the input object just after that lens. It means that this object will be illuminated by the converging wavefront. And you look at the longer dotted dashed lines which originate from the object and end at the image plane. So this indicates that a point at the object will be focused at a point on the image plane as indicated by the long dashed line. And you see that this optic axis is passing through the center of all the components, that is the center of the lens 1, the center of the lens 2, and also the center of the object plane. So you see that this technique will also enable us, that is the illumination of the object with converging wavefronts will illuminate us to remove the quadratic phase factor associated with the object plane. So this is the imaging system for removal of object plane quadratic phase factor. So again, let me remind you that this is on the left hand side in equation number 77 is the quadratic phase factor. So this is also removed by the second option that we have described over here using this diagram. Now if the phase contribution by the object quadratic phase factor in a small region of the object that contributes at a particular image point is a small fraction of a radian. So you see that this is the second possibility that can help us to remove the quadratic phase factor, and is that is the region of the so let me explain through that one through this diagram. Look at the diagram on the left. So you see that there is a point on the object at the zeta eta plane, and that is passing through the lens and is being focused on the UV plane, and you know that the focusing point is not as sharp as the object point, but it is a blur image. So this is a blur image, you know that. It means that a sharp object point will be focused by an optical system to a blur image point. So now look at the second diagram. So if you have a small sharp image point, trace it back through the same optical system backward on the object plane, and you will see that it will indicate a region of the object that will contribute to obtain the sharp image point at the UV plane. So this small region on the object, if the phase variation in this small region is less than 1 milliradian, then you know that the quadratic phase factor is also removed. So let's read the description. On the right hand side image, an ideal image point is traced backward through the imaging lens and mapped to a portion of the object. If the phase variation in the object region is a small fraction of a radian, the contribution from the quadratic phase factor in the object plane will be small and can be expressed in terms of the parameters of the image point. So you see that the contribution of the phase variation in this small region is less than a fraction of the radian. Then you know that we can use this description, this transformation that we are going to describe in equation number 77, that the quadratic phase factor associated with the object plane, that is e to the power iota k over 2 z1, and within the parentheses we have zeta square and eta square, can be replaced by an equivalent quadratic phase factor associated with the object image plane, that is e to the power iota k over 2 z1 into u square over m square plus v square over m square, where m is the magnification of the system defined by m is equal to minus z2 over z1 is the magnification of the system. Under this transformation of equation, equation number 75 and 77, which we have described in the previous slides, can take the following form. So you see that this is the kappa, this is kappa as a function of u and v, and you know that we have defined the kappa as the impulse response of the system, and then you know that in this you would see that e to the power, that the quadratic phase factor associated with the object, that is this one, e to the power iota k over 2 z1, within the parenthesis we have zeta square plus eta square, is not present, but we have replaced that one with e to the power iota k over 2 z1 within the parenthesis u square over m square plus v square over m square. So you see that quadratic phase factor is not present in the kappa, in the impulse response system of as given in equation number 78. And you know that otherwise this has to be present within the Fourier transform, within the curly bracket on which the Fourier transform operator will operate. Okay, now you see that we can similarly write down the field calculation using the condition given in equation number 77, and the equation number now 76 will take the following form as given in equation number 79. Again you will see that the quadratic phase factor associated with the object plane, which otherwise was present in the curly bracket on which the Fourier operator was operating, is no more in that curly brackets, but it is outside the integral sign, and you know that you will see that it is outside the integral and is e to the power iota k over 2 z1, and within the parenthesis we have u square over m square plus v square over m square. So you will see that in equation number 78 and 79 the quadratic phase factor associated with the object plane is no more present under the condition that we have described in this paragraph. Okay, if we apply the transformation given in equation number 77 and introduce the magnification parameter m and omit the quadratic phase terms at the object plane and a constant phase term also, and setting zeta naught equal to and zeta naught replaced by zeta and eta naught replaced by eta, the impulse response given in equation number 69 is simplified as given. So you see that this is what we have written, the impulse responsible in the simplified form from equation number 69 using the transformation that is given in equation number 77. So you see that in the next step what we have done is that we have omitted the constant phase factor, which is e to the power iota k multiplied within the parenthesis z1 plus z2, and also we can get rid of iota square in the denominator, and this is again the impulse response transfer and the impulse response of the system following the above statement. So you see that this form is an ugly form, so we want to write it down in a useful form, and for that one we are going to introduce the parameter m, that is the magnification of the system. And you see that here we have introduced m over here. M, what is m? M is equal to minus z2 over z1. If you place the value of m over here, you will see that the z2 in the denominator will be cancelled out and will be replaced by z1. So you see that we have again the previous terms as in the exponential in the above integrals. In the above expression. So you see that here we have introduced the parameter m, and you will know that in the second exponential, which is e to the power minus iota k, within the curly bracket we have all the terms in the denominator which is z2 dependent, and we can take z2 common from all these terms, and then we can write this kappa in the next step as in equation number 80. So kappa of uv semicolon with the zeta and eta is of the order of, you see that here we have constant term 1 over lambda square z1 into z2, and within the integral we have a p of xy, and you know that the exponential form is now in a beautiful form, that is e to the power minus iota 2 pi over lambda z2, and within the curly bracket and of course within two parentheses we have u minus m times zeta multiplied by x, and within the parentheses v minus m times eta multiplied by y, and the integration is with respect to x and y. So this is in equation number 80, and you know that here the quadratic phase factor is also not present because we have omitted that one. Okay. So no more quadratic phase factors associated with the image plane, that is u square and v square, they are not present. So what we have assumed in writing equation number 80, let's read these assumptions that under which the equation number 80 was produced. Number 1, the constant phase term was dropped. For example, this constant phase term e to the power iota k within the z square plus z2, that has been dropped, and you know that this was constant, so we have dropped that one. The other one is that the phase variation in the object region that contributes at a small ideal image point is a small fraction of a radian, and the quadratic phase term at the object plane was transformed to the quadratic phase term at the image plane. So you see that under this condition, that is according to figure this one on the right hand side that we have just described, we can use this transformation as given in equation number 77, that is the quadratic phase factor associated with the object plane can be replaced by the quadratic phase factor with the image plane. The third condition is that the two quadratic phase term in image coordinates were omitted, which can be justified by saying that the quantity of interest is the image intensity, or by measuring the image field at an appropriate spherical surface. So let's talk about these two quadratic phase vectors which are associated with UV coordinates, that is at the image plane. We have omitted e to the power iota k over 2 z1, and within the parenthesis u square over m square plus v square over m square, and multiplied by e to the power iota k over 2 z2, and within the parenthesis we have u square plus v square. We have omitted these two quadratic phase vectors on this basis that we shall be interested in the intensity, and you know that when we shall write down the intensity relationship, then of course these two quadratic phase vectors being a complex will automatically be eliminated from the expressions. And if you talk about the amplitude or at the image plane, where you have to where you cannot remove these one, only in the case that you are measuring the field at the image plane on a spherical surface. If you assume that your imaging plane is a spherical surface on the image plane, then you know that these two quadratic phase factors will also be removed, as we have explained in step number 3. Number 4, the magnification parameter factor m of the system was introduced in the integral. So you see that we have introduced in the integral over here, that is from this step to the step given in equation number 80, that we have introduced the parameter m. Number 5, the geometric imaging equation for the lens is satisfied by choosing appropriate value of the image distance z2. So you see that in our previous analysis, in the previous you know that slide number 54, we have replaced 1 over z1 plus 1 over z2 is equal to 1 over f, or 1 over z1 plus 1 over z2 minus 1 over f is equal to 0 was set up, and that was the geometric imaging equation was also satisfied for an appropriate value of z2. So choose z2 in such a way that the equation 1 over z1 plus 1 over z2 minus 1 over f is equal to 0 is satisfied. And you know that the quadratic phase factor was also removed by choosing an appropriate value of z2. Now the presence of a parameter m makes equation 80 for space variant system. So you see that this equation is written for a space variant system because of the presence of the m. We cannot write, if m is not present, then you see that we have u minus zeta and v minus eta, because if m is a unity or m is not present, then this equation will hold for the space invariant system. But you know that due to the presence of the system, the equation will hold for a space variant system. For a unit magnification where m is equal to 1, the system will turn up into a space invariant system for which the kappa can be written as that kappa of u comma v semicolon zeta comma eta can be set equal to kappa of u minus zeta and v minus eta. Then you know that if you set m is equal to 1, then you will have in the expression as u minus zeta within the parenthesis multiplied by x and plus v minus eta multiplied by y, because m is equal to set m has been set equal to 1, and then you see that equation 8 will then hold for a space invariant system, under which condition the kappa can be written as kappa of u minus zeta and v minus eta will replace kappa of u comma v semicolon zeta comma eta. But you know that in our case m is not equal to 1, but we can convert equation 80 to hold for a space invariant system if we use these transformations, that is zeta with the inverted hat is equal to m times zeta and eta with the inverted hat is equal to m times eta. So let's make these transformations in equation number 80. Then we shall get the following equation as we have shown in equation number 81, that is kappa of u minus zeta inverted hat comma v minus eta inverted hat is of the order of 1 over lambda square z1 over z2 z1 into z2, and the double integration is on p of xy, and you know that the exponent is also written without the involvement of the magnification, because the magnification is implicitly involved but is not explicitly involved in the expression of e to the power minus iota 2 pi over lambda z2, and within the curly bracket we have u minus zeta inverted hat multiplied by x plus within the parenthesis v minus eta inverted hat multiplied by y, and the integration is with respect to dx and dy. You see that here m is not present, and you know that this kappa has been written in equation number 81 for a space invariant system. And you know that the space invariant system is the system in which kappa will not change its functional form. It can change from point to point on the image plane, but you know that the shape of the kappa will not change, which means that we are talking about the space invariant system. Okay, in order to remove the scaling constants lambda square z1 and z2, for example, you see that these scaling factors are also present, and if you want to get rid of these scaling factors as in equation number 81, that is lambda square into z1 and z2, we introduce the scaled coordinates at the pupil plane through the following transformations. So here x prime is equal to x over lambda z2, and so ultimately dx is equal to lambda z2 into dx prime, and y prime is equal to y over lambda z2 will give you dy is equal to lambda z2 into dy prime as in equation number 82. So if you make these modifications in equation number 81, you will get the following equation as given in equation number 83, that is kappa of u minus zeta inverted hat comma v minus eta inverted hat is of the order of z2 over z1, and the double integration, and you know that here the pupil function now has been modified as with arguments that p of pupil function now has the coordinate lambda z2 x inverted hat comma lambda z2 y inverted hat. And you know that the exponential function is e to the power minus iota 2 pi over lambda z2, and within the curly bracket we have u minus zeta prime multiplied by x plus v minus eta v minus inverted hat multiplied by y, and then integration variables dx and dy. But you know that we can introduce, we can take, we can remove z2 and z1 on the other side of the equation, on the left hand side, and we can introduce the parameter capital M as the magnification, as the magnitude of the magnification. And in that case we can use equation 84 because on the left hand side we can replace kappa. Now you know that we have written it as kappa inverted cap, inverted hat. Kappa inverted hat is equal to u minus zeta inverted hat comma v minus eta inverted hat is equal to kappa of u minus zeta inverted hat comma v minus eta inverted hat divided by the absolute value of the magnification. So you see that if you introduce this one in equation number 83, then we can get equation number 85 that has no you know that constant terms present in this integral either on the left hand side or on the right hand side. And you know that on the left hand side we have kappa inverted hat with coordinates u minus zeta inverted hat comma v minus eta inverted hat, and you know that this is approximately equal to the double integral from minus infinity to plus infinity. And then you know that the pupil function has the arguments, has the coordinates, that is lambda z2 x inverted hat comma lambda z2 y inverted hat, and then you know that in the exponent we have e to the power minus iota 2 pi over lambda z2 and u minus zeta hat multiplied by x and v minus eta hat inverted hat within the parenthesis multiplied by, and of course then. So you see that equation of 85 is the most simplified version of previous equations, because you know that no constant phase terms are present, no constant terms are present within the integral or outside the integral. Only the terms are present within the integral which are integrable with respect to x and y coordinates. But you know that here we should also have introduced, actually this is dx prime and dy prime, not only dx and dy, and I think that we have also here x should be replaced by x prime and y should be replaced by y prime, as because we have introduced here x prime and y prime. So you see that make some correction in equation number 5, that dx we have dx prime and dy prime, and similarly in the exponent we have x prime and y prime, and similarly we have as we have in p of lambda z2 x inverted hat. So x inverted hat should also be present all around, and the integration is also with respect to that inverted hat. Now you see that introducing the transformations that I have made in equation and which we have displayed in equation number 82, we have now introduced correctly in equation number 83. And you know that you have x prime everywhere. So we have the pupil function with the arguments lambda z2 x prime comma lambda z2 and y prime, and similarly in the exponent we have e to the power minus iota 2 pi over lambda z2, and within the curly bracket we have a parenthesis u minus zeta multiplied by x prime plus v minus eta inverted hat, and this factor was multiplied by y prime, and the integration is now with respect to dx prime and dy prime. And similarly you see that when introduced kappa inverted hat through equation number 84 to the equation number 83 was written as given in equation number 85. So in equation number 5 you will see that no constants are present, no phase factors are present, and now the integration is also with respect to dx prime and dy prime, and you know that x prime is contained in the pupil function lambda z2 x prime comma lambda z2 y prime, and y prime is also indicated, and you know that also in the exponent form, that is e to the power minus iota 2 pi over lambda z2. Within the curly bracket we have u minus zeta inverted hat whole multiplied by x prime plus v minus eta inverted hat was multiplied by y prime. So you see that this is the modified this is the modified impulse response of the system with the kappa inverted hat containing u minus zeta prime and v minus eta prime. So you see that since we have a modified equation number 85, and you know that kappa will be used in the imaging equation which we are going to present next. And now we first transform the imaging equation number 60 for the space invariant system, and then introduce the scaled variables that we have already introduced above, that is zeta inverted hat is equal to m times zeta and eta inverted hat is equal to m times in eta. The previous equation, you see that for a space invariant system was that is the image intensity, that is the field at the imaging plane ui as a function of u and v is equal to double integration, and u naught contains u naught as a function of zeta comma eta, and kappa was multiplied, kappa was written for the space invariant system, which is a kappa of u minus zeta and comma v minus eta d zeta and d eta. So introducing the above transformation, that is zeta inverted hat is equal to m times zeta and eta inverted hat is equal to m times eta, we are introducing this one and we obtained the second step over here. And you know that in the second step we have zeta inverted hat over capital M as an argument of the u naught, and similarly eta hat divided by m as a second argument of the field u naught. And similarly you can see that we have kappa, we have in the kappa u minus zeta inverted hat and v minus inverted eta hat, and similarly d zeta and d eta have been replaced by d zeta hat inverted hat over m and d eta inverted hat over m. So you see that the purpose of modification this one is that we can introduce equation number 80 into the imaging equation, that is we can write kappa inverted hat over there. So what we do is that we divide this kappa by the factor m mod, and the rest of the quantities are shown as such. Then you know that in the next step, that is in the last step of equation number 86, we have written in the curly bracket 1 over m mod multiplied by u naught with arguments zeta inverted hat over capital M comma eta inverted hat over capital M. This is contained in the curly bracket, and now you see that we have introduced the kappa inverted hat over there as using equation number 84. We have introduced the kappa inverted hat in the last step of equation number 86 as a kappa inverted hat is equal within parenthesis u minus zeta inverted hat comma v minus eta inverted hat and d zeta inverted hat and d eta inverted hat. And you know that then this is the imaging equation for equation number 86, and if you want to, now you can introduce the kappa from equation number 85, and you can introduce the kappa very simply in equation number 86 to get the full expression for the imaging intensity for the imaging field at the image plane. For the moment, assume that kappa inverted hat u minus zeta inverted hat comma v minus eta inverted hat represents a perfect image of a point source located at zeta inverted hat comma inverted hat. Then you know that if it is a perfect image, we can set it equal to delta. So kappa has been set equal to delta of u minus zeta inverted hat comma v minus inverted hat in equation number 86. Then equation number 86 will take the form as given over here in the last step of this. So ui of u comma v double integral within the curly bracket, we have the same term as above, and you know that we have replaced kappa inverted hat with the delta of u minus zeta inverted hat comma v minus eta inverted hat, and the integration variables are the same. So you see that if you solve this integral, what will you get at the end as it is given in equation number 87, that you will get ui of ui, that is the field at the imaging plane as a function of u comma v is equal to 1 over m mod, which is the absolute value of magnification, multiplied by u naught u over m comma v over m, because we have to replace u with zeta prime, that is the zeta prime, that is the zeta inverted hat will be set equal to u, and inverted eta hat will be set equal to v according to the delta function arguments. So the arguments of the delta functions will replace the zeta prime and eta prime in u naught. So zeta prime in the as an argument of u naught, and eta prime also, and eta inverted hat also as an argument of the u naught will be replaced simply by u and v. So at the end we have in equation number 87 simplified version of the imaging equation, and you know that we can set this term, that is 1 over m mod u naught of u over capital M comma v over capital M is equal to ug. This can be classified as ug of u comma e, and ug stands for it is an ideal image or the geometrical optics image, because we have assumed that the kappa is very sharp. So you see that the image obtained under that condition will only involve the magnification factors, and you know that this the imaging, the field at the object plane will be equal to the field at the imaging plane, except that the magnification of the system will be involved, and such an image also is referred to as the ideal image or the geometrical optics image, as given in equation number 87. So introducing UG of U comma V into equation number 81, we obtained the following results. So you see that now we have replaced this factor in equation number 81, that is, we have introduced the ideal image or the geometrical optics image in the equation number 81, and then we have written. So this is equation number 81, you see, and there we have introduced this is the kappa, and you know that we can we can modify the imaging equation to write over results, which we are producing over here in equation number 88. So the field at the image plane as a function of uv is equal to the double integration, and the field and the double integration contains uj, which is the geometrical optics image as a function of uv multiplied by kappa inverted hat with the arguments u minus zeta inverted hat comma v minus inverted hat eta inverted hat, and the integration variables z eta d zeta inverted hat and d eta inverted hat, and the symbolic form of this integral is given in the second step of equation number 88. So in the symbolic form we can write that ui, that is the field at the imaging plane, is equal to the uj convolved with kappa. So this is in the form of convolution that we have written, because the above integral is the convolution integral between ug and kappa inverted hat. So this is what we have written in equation number 88. So the imaging intensity at the image plane, the field at the imaging plane will be equal to the geometrical optics field at the image plane convolved with the kappa of the imaging system. So this is the image UG is a diffraction free image, and the real image U and the real image field UI includes diffraction and is a blur version of UG. So in this equation 88, UI is a blurred version of UG due to the convolution with the kappa. So convolution thus introduces blurriness into the images. The image intensity expression can be written in the following form. So image intensity, you see that if you want to obtain the image intensity, you can write I as a small I as a subscript stands for the imaging plane. So this is the intensity expression, which is equal to the product of UI multiplied by its complex conjugate, and you know that we can simply write it as the absolute square of the UI as a function of UV. So you see that calculating the intensity information expression from equation number 88, we can simply write the absolute square of the integral there, and also the absolute square of the symbolic form of that expression. So the intensity on the left hand side is equal to the absolute value, absolute square of the integral which we have described above, and also the absolute value of the convolution between UG and the kappa. Impulse response of the system in more simple form. Now to write the impulse response of a system in a more simpler form, let's assume that A is the strength of the point source located in the object plane at the coordinate zeta and eta. So you see that before we started over this expression, all these expressions were started when we assumed that a point source existed at the zeta and eta plane, that is the input object plane. Now you see that we are assuming that the strength of that source is represented by small a. Amplitude of the spherical diverging wave incident on the lens and originated from the point zeta and eta is equal to A over lambda z1. So you see that the lens is located at a distance z1 from that point source, and the strength of the diverging wave at that of the diverging wave incident on the lens is A is equal to A, capital A is equal to small a over lambda z1. Field just before the lens located at the xy plane from equation number 60 is now written written as UL, that is the field just before the lens, as a function of xy is equal to a multiplied by e to the power iota k z1 over iota lambda z1 and e to the power iota k over 2 z1, and within the curly bracket we have x minus zeta square plus y minus eta square. So you know that this is the field which is just incident on the lens, or the field just before the lens. Now dropping the constant phase factor and the complex number iota and introducing a over there, we can write equation number 91 as that is the field just before the lens is approximately equal to a e to the power iota k over 2 z1 multiplied by within the curly bracket and within two parentheses we have x minus zeta square plus y minus eta square. Field at the image plane located at the UV plane from equation number 81 can now be written as, so you see that we have written this expression for the field from equation number 81, that is kappa of u minus zeta inverted hat v minus eta inverted hat is approximately equal to a over lambda zi. Here we have introduced zi because we have replaced z2 by zi, because z2 is the image plane distance, and similarly we have replaced by z2 by zi, and zi is the imaging distance from the lens. And you know that we have all these expressions the same as we have obtained earlier, except that we have p of x comma y, and then you know that we have e to the power minus iota 2 pi over lambda zi. z2 has also been replaced by zi, and the rest of the terms are u minus zeta inverted hat into x plus v minus eta inverted hat into y, and the integration is again with respect to dx and dy. In writing equation number 92, we have replaced z2 by zi. And similarly we can do the same thing, and then we can express this one in terms of the magnification also, that is we can revert the z eta inverted hat with m times zeta, and zeta inverted hat is equal to m times zeta, and eta inverted hat is equal to m times eta has also been introduced in equation number 93 with the original parameters, with the original zeta and eta coordinates. So you see that this states that the field about an ideal image point located at u is equal to m times zeta and v is equal to m times eta is simply the Fraunhofer diffraction pattern of the impulse of the lens pupil function with point source located at zeta and eta. So let me read once more, because this statement is very important. This states that the field about an ideal image point located at u is equal to m times zeta and v is equal to m times eta. Here we are talking about the ideal image point located on the image plane at these coordinates is simply, so the image there, that ideal image point we are talking about is simply the Fraunhofer diffraction pattern of the lens pupil function with point source located at zeta and eta coordinates, and zeta and eta are the input coordinates where we have placed our original source that we have defined over here. So you see that more Fourier optics will be coming in the next slides. So this is the end of slide number 55.